Greetings. This is Fadi Dawoud. On behalf of teammates Habiba Gamal, Eslam, Soliman, and Mohamed, I'd like to welcome you to our presentation. Today, we will first talk about our motivations and objectives for the project, followed by the overview of the project itself. Next, we will discuss our empowerment outcome before getting into the project design along with our operating assumptions. An overview of the technical specifications is given afterwards, and next, experiments and the results will be discussed, and finally, a demo of the system will be presented. So let's start at the beginning, our motivation for this project and its objectives. Our motivation for this graduation project comes from the vast growth of the internet. Tens of billions of nodes scattered all over the web generate data at the rate of several exabytes every single day. Imagine the untapped potential in this vast amount of data. Yet it remains untapped because most of this data is private and solely owned by a single entity. It is both difficult and complicated to share private data among multiple parties securely. And we all have heard of the lawsuits against major internet corporations over data privacy. What we end up with is that each node only has a limited amount of data that it owns. Any one node could create a machine learning model and train it over this narrow amount of data. The node is unable to collaborate with a neighbor node to produce a better model because both nodes are worried about the privacy of their data. It is an instance of the prisoner's dilemma. The collaboration between nodes would lead to a positive outcome, but the nodes are unable to entrust each other with their private data. So a solution is needed. The solution must allow these nodes to work together and collaborate on training a single model using all of their data without sacrificing their privacy. It also must be decentralized such that no central authority must exist to regulate this collaboration. It must be fair such that nodes will be rewarded on their collaboration based on their contributions. And finally, this solution has to be efficient in terms of computation and communication. For our graduation project, we set out to implement this solution. This section is an overview of our work. We created FLOBC, a framework for federated learning over a blockchain. Essentially, it is a machine learning system that is currently able to support any machine learning model that is based on gradient descent. This covers the vast majority of popular machine learning models, such as support vector machines and neural networks. The system expects a number of agents, called trainers, to perform local training on their private data and only submit the results of this training to be considered into the final model. The system is built over blockchain. One reason we chose blockchain as the backbone of the system is that it provides the decentralization needed for the solution, eliminating the possibility of a single point of failure. Additionally, its inherent system of request validation and voting-based consensus provides an infrastructure for evaluating training updates and keeping records, ensuring more decentralization in training as well as fairness. Finally, it preserves the identity of the trainers behind hashed pseudonyms, protecting their privacy further. More technical details on these different aspects of the system are to follow shortly. We built this machine learning system as a sandbox for experimentation. We have created scripts that simplify the process of tuning, running, and recording the training performance of the system. We have also created a graphical user interface to monitor the system operation. This sandbox, along with the helper scripts, were used to perform a number of experiments that will be reported later on in the presentation. We believe our work could possibly be a significant step into collaborative, privacy-preserving machine learning, which would allow us to build very powerful models in the future. But in the meanwhile, let us look at the empowerment outcome of our project.
As for our empowerment outcomes, our project is considered to be a proof of concept for the validity, benefits, and performance of a decentralized machine learning system. We have a completed research paper draft that includes our methodology, experiments, results, and the conclusions. And lastly, we implemented some automation tools and software for validating and re-evaluating our results, in addition to using the system in general. These tools include both automation scripts and simple graphical user interface presented in a web client. Consequently, we consider submitting the research paper in one of the following two conferences. The first is the IEEE ICDM for data mining, and the second is the New York IPS for machine learning and computational neuroscience. Feel free to take a look at our paper by scanning the QR code presented in the slide and send us your feedback if any.
Hello everyone, my name is Mohamed and I'm going to walk you through our design methodology and assumptions. So let's start with a high-level view of our system. In a real-world scenario, prior to the formation of the setting, a node proposes to the network a new model to which other nodes subscribe either as trainers or as validators, which then leads to this architecture shown in the diagram. The yellow nodes around the edges represent trainers, each having their own private data that they use for training. The green nodes represent validators, which act as decentralized maintainers and gatekeepers for models on the system. All produced models are stored over the blockchain, whose consistency is achieved through voting consensus between validators. Validators vouch for models based on how they perform on their own validation datasets. Each validator evaluates every update transaction done by a trainer, assigns it a score, and then decides whether it should be accepted or not. Scores given by validators are then used to evaluate trust levels of different trainers based on the quality of their work. So the arrows you see correspond to three types of actions. Solid purple represents a trainer sending a model update to a validator. Dotted green and red lines represent the validator adjusting the trust score associated with a certain trainer. So next I will be giving more details about different aspects of this design and their overall implications. Now, first and foremost, our system is both model and data agnostic, meaning that the model structure along with the data it's being trained or validated on are not part of the system design itself, but are rather a form of pluggable externals. However, the only assumption that the system makes about the model is that it's compatible with gradient descent optimization. That being said, it is quite feasible to incorporate other optimization methods into the framework as long as their progress can be quantized into a canonical representation, such as the gradient vector in case of gradient descent. By virtue of this model agnosticism, hosting or training a new model on the system is as simple as plugging in two scripts that describe the model, one for trainers and another for validators, assuming of course that their corresponding data exists somewhere. And of course, no data sharing is ever needed throughout the whole process, as we only share insights, not data. We now move on to Byzantine fault-tolerance. The term Byzantine refers to a range of undesired node behaviors that occur in distributed systems, such as leeching, maliciousness, or simply being offline during a crucial time. The way we deal with such behavior is through our reward-penalty policy, which enables the system to handle Byzantine trainers and generally improve model production quality. So under this policy, each trainer is assigned a trust score phi, which translates to how reliable or trustworthy that trainer is. Phi is a factor between 0 and 1 that is used to weight the respective trainer's updates, and that achieves two things. First, it ensures that we get a standard weighted average of all updates. Secondly, it creates inherent competition to the system, as any rise in a trainer's score would result in a relative decline for other trainers and vice versa. On that basis, some scenarios result in a trust reward, and the main ones are improving model performance or merely performing better than the competition. Other scenarios, however, result in a trust penalty, such as degrading the model, losing to competition, or being abstinent altogether. We now arrive at one of the most central aspects about our design, which is training work synchronization. So what happens is that we have multiple trainers training on their own data, starting from ideally the same base model checkpoint. And after they progress with their independent local training, a synchronization barrier is posted at which all available unsynced updates are aggregated to create a new model checkpoint. From that new checkpoint, a new training round starts, and so on, as shown in the diagram. Synchronizing updates is quite important because aggregating off-sync updates together may result in parameter degradation. So towards that end, we have adapted three synchronization policies that are quite common in parallel computing. They are bulk synchronous parallel, stale synchronous parallel, and barrierless asynchronous parallel. It might be a bit lengthy to explain the inner workings of each of them, but it suffices to say that they exist on a trade-off spectrum on the degree of synchronicity. Higher synchronicity means trainers are more in sync with their model checkpoints. On that spectrum, BSP has the highest synchronicity as training proceeds in bulks with strict deadlines. Under BSP, each trainer is allowed to submit only one update during the same round, which incentivizes trainers to be careful not to undertrain and risk a bad score, or overtrain and risk missing the deadline altogether. So missing the sync barrier deadline puts late updates at a disadvantage, because they would be evaluated based on the new model, not the one that they actually started from, making them more off-sync. SSP is a compromise on BSP, in which deadlines are more relaxed to accommodate slower trainers through deadline extensions, during which faster trainers are allowed to keep training for a specific number of times. BAP is the exact opposite of BSP, as trainers are allowed to train non-stop, and updates are synchronized whenever a minimum portion of trainers have unsynced updates, which is the complement of the slack ratio, or the ratio of trainers that have not yet submitted their work. Finally, it's time to discuss some major assumptions and caveats related to our methodology. First, it's important to note that the quality of models produced through the system is limited by three main things. The collective data used in training and validation. Our methodology can help isolate bad data, but it cannot create good data. overall level of honesty of system nodes, trainers, and validators alike, our framework can deal with Byzantine behavior as long as it's not a majority. Finally, model structure and the training algorithm employed by trainer nodes. Our framework does not optimize model structure nor its training algorithm. The second major assumption is that validator datasets should be sufficiently positively correlated in order to reach a fruitful consensus. This is important as validators act out like a jury, so if they all have completely different ideas of what a good model is, then they won't be able to agree on one. Thirdly, strictly more than 2/3 of validators should be non-Byzantine. This is also a consensus requirement, but it's posed by the Exonym blockchain framework itself. Validators should also be partially synchronous, which means that their computational capabilities are comparable. And last but not least, the underlying network should also be partially synchronous, meaning that all messages are delivered after a finite, yet potentially unknown time window. And now moving on to some of our technical specifications. So here I'm going to briefly present our implementation technologies. We have utilized the following frameworks. First, we use Exonym as our blockchain framework due to its customizable voting-based consensus, and we also use Node.js for light clients such as trainers and other helper subroutines. Moreover, our graphical interface is also a Node.js-based React web application. As for programming languages, we mainly use the following three. We used Rust for developing our blockchain infrastructure along with validator nodes. We used JavaScript for developing light clients and their interfaces. And for machine learning related aspects, we primarily used Python due to its richness and useful machine and deep learning libraries. Finally, we rely on shell scripting for automation and spawning system nodes.
As for our experiments, we used a convolutional neural network on the MNIST dataset to classify handwritten digits. We have 4 experiments that include an extra one since our last presentation. The first one is the Trainers-to-Validators ratio experiment, in which we aim to understand the effects of changing the numbers of trainers and validators in the training topology on the model performance and growth rate. Our initial hypothesis is that more trainers will result in a higher performance and faster growth. However, more validators will provide higher trustworthiness. So it's more important to find the best ratio that achieves the best model quality without compromising decentralization. For the experiment setup, we have gone through 9 runs, all of them with 10 participating nodes, but after each run we increase the number of trainers by 1 at the expense of the number of validators. Each run goes for 30 training iterations using BAP as a synchronization policy, while measuring the highest accuracy reached and the number of rounds it takes to reach this accuracy. According to the result graph, the best configuration is to have 70% trainers, and this configuration achieved 98.74% accuracy. For the second experiment, the objective is to test and confirm whether having a reward penalty policy provides significant performance improvement. We have a configuration of 6 trainers and 3 validators, using BSP as a synchronization policy and running the system for 30 rounds. For this experiment, noise is applied on updates of different trainers, relative to their index. For the first trainer, no noise was applied, and the noise is increased gradually till we reach the maximum amount of noise applied on the updates of the 6th trainer. We had 2 runs, only one of them was applying the reward penalty policy by giving trainers scores on their updates. In the following table, you can see each trainer scores after a certain number of iterations. For the most 4 affected trainers, shortly after starting training they have been penalized by a 0 score. As for the other 2 trainers, they have been allowed to participate in the training with more reward for the first trainer who has no noise applied on its updates. The second part of the experiment is to compare the scoring group with the control group, which had no scoring policy. We have noticed that trainer scoring improved the performance, stability, and convergence speed of the model, as only the updates from the high-performing trainers were taken into consideration and contributed to improving the model. In the third experiment, we compare the different synchronization schemes, which are bulk synchronous parallel (BSP), stealth synchronous parallel (SSP), and barrierless asynchronous parallel (BAP). The objective of the experiment is to determine the best synchronization scheme on both model growth and average time per training iteration. We have 2 comparisons. The first is comparing the performance of the different schemes through 30 training iterations. The second is to compare the progress after 20 minutes of training. Note that we have 2 variants of BAP. BAP 100 with a majority ratio of 100%, which also means a slack ratio threshold of 0%. The other variant is BAP 60, with a majority ratio of 60%. The ideal scheme in terms of performance will start the graph at the highest accuracy possible, which is 100%. So as you can see on the graph on the left, BAP 100 is the closest to 100%, and as a result, it offers the best performance because it has the best utilization for trainers updates with 0% slack, followed by SSB and BAP 60 with more consistency in SSB, and BSP at the bottom as it offers the strictest synchronization policy. As for the progression speed, you can see on the right that BSP is the fastest by releasing an average of more than 1.2 models per minute. It is the strictest in terms of deadlines, followed by SSB, which is a compromise between performance and throughput, and at the bottom, the two BAP variants, with BAP 60 as the faster scheme because it allows a slack ratio of up to 40%. For the newly added experiment, we compare the performance of a traditional centralized machine learning system with its counterpart, a decentralized system such as ours. We expect both systems to have similar performance, more specifically to converge to approximately the same accuracy after few training iterations. The setup of this experiment is a configuration of 7 trainers and 3 validators, which is the best configuration according to Experiment 1, with activating the reward penalty policy. And as expected, the centralized model had higher accuracies than the decentralized alternative for 10 iterations, after which the decentralized model managed to evaluate the trainer's updates and allowed higher contribution to the model. Then both systems converged and reached approximately the same accuracy. This experiment shows that the added benefits of decentralization and privacy-preserving training do not degrade the model performance. These results are not meant to demonstrate that the decentralized version is superior in performance to its centralized counterpart, but rather it shows that the two are closely comparable in that regard. And now I'll be leaving you with Habiba for our technical demo.
So now for the demo, we've created the simple GUI to facilitate running and visualizing the system. This GUI is not meant to be used by a single trainer or validator, but rather to run the system as a whole, specifying the number of trainers, validators, and sync scheme. This GUI can also be displayed in light mode. Now I'm going to select the directories containing the training scripts and validation scripts. These fields would allow other researchers to try their own models using our system. In this system run, we will be using BAP for the sync scheme. We will be using 7 trainers, 3 validators, and we will stop after 15 iterations. The difference in the noise between each trainer and the next will be 0.1. So the first trainer will have noise of 0, the second one will have 0.1, the third one will have 0.2, and so on. Right now, the validators and trainers are being built and started. Then we will be able to monitor the change in accuracy and the trust scores. Note the changes in the pie chart. The trust scores of some trainers are becoming lower and lower each iteration until the updates of some of them no longer count. Of course, this part of the demo is sped up to fit the time frame. As you can see right now, the updates of only 4 trainers count, and there are 3 trainers with trust scores of 0 because of their noise. Now all 15 iterations are complete. As you can see, the accuracy was increasing drastically at the beginning and then it plateaued near the end. It started with accuracy 67.97 in iteration 1, reaching accuracy 98.26 in iteration 15. I hope you've enjoyed this short and simple demonstration of our system. Thank you.